readings. In this one, I'm gonna be doing something with this function that's called f. So this function is equal to xy squared plus yx squared. Yeah. Plus yx. And I just called it f, but properly you could say f of x and y. I'm not doing it to save a lot of space. I'm just writing f, although it's f of x and y. Just like with partial derivatives, we won't use the delta notation or and so on. We will really use only subindexes of f. So I will do f sub small x to denote a partial derivative in respect to x, the same for y. And second partial derivative in respect to x is f sub xx, the same for y again. Mixed is f sub xy. So this function is a multivariable polynomial, and I want to find first of all the extreme points of it. So I'll show in a second how to do that. And then there's a theorem that tells you if these extreme points or these critical points, if they are a local minimum, a local maximum, or a saddle. So we'll see how many points we first get, and then we'll see how to take these points and evaluate them in particular instances of algebra calculations in order to find what they actually are in the context of the function. So the way you find critical points is similar to finding them if a single variable function, but here we have two independent variables, and the way I do it is here. You take the function and do a partial derivative in both of the, in terms of in respect to either of the variables. So first in respect to both of them actually. So first we'll do partial derivative in respect to x, and we'll also get a partial derivative in respect to y to gain some information about it. And that will be set to 0, and it will create two equations in respect to x and y, and the solution for x and y, we'll see how many we get. And those solutions, those pairs x and y, will be put into the coordinates of points, and you'll see how many points we can find. So that's basically it. We'll get two equations in terms of x and y. We'll solve for x, then thereby we'll solve back for y, and we'll get actually 2 points. I already calculated, so I know we'll get 2 points, 2 different points out of this. 2 values for x and y. So let's start with that. Partial derivative in respect to x is y squared plus 2xy plus y, and partial derivative in respect to y is 2yx. Very similar, but the same idea is repeated for x instead of the y's, plus x. So you see this term is completely the same, but these two are different. The y squared and y is then x squared and x for the partial derivative of x and y respectively. And so we get this, and then both of these I set to 0, just like you would set to 0 the first derivative of a normal function only in respect to one variable. But here we have two, so we did partial ones in respect to both of the variables separately, and then we set both of the equations to 0 separately. Now from this, for example, I'm going to show you how to proceed, but I'm not going to do the whole calculation here because it would take up the whole screen. I'm going to skip that. I'm going to have the results in a second afterwards. I'm just going to show you how to approach it. So basically, what I could do, and that's how I get it, is basically this. Let's take one of the equations and see. Everything is y except one instance of x, so I'll solve for x from the f sub x. So I will have 2xy first equals, I will subtract the other two terms, and then divide both sides by 2y to get minus y squared over 2y. So I solve for x, and this exact x I put into the other equation, into the f sub y. So I put it there, and I solve for this time already y, and I'll get numerical results for y. I'll get 2y. So y is 1. The first result of y will be minus 1. Second result will be minus 1 over 3. Minus. And then once I get that, I will put it back into the equation. And so I could put it back into one of the equations we have. For example, you could put it in the Well, we could have just used the x in terms of y that I just deleted. But you could also put it, for example, here. And so then you will solve for the x. So first use -1, for example, then use -1/3. And for both of them, you will get a different x1 and x2. So for y1, if you plug in y1 here, you will solve for x1 and you will find a point. So the y1 we already knew had the point -1 for y. The second y2 created the y coordinate to be -1/3. And then the x coordinates here are yielded from this equation, and that will be respectively 0 for the -1 and -1/3 as well for the -1/3. So these are the results. So these are points 1 and point 2, point 1 and point 2. So I'll write them here. So point 1 is 0, -1, and point 2 is x equals -1/3 and y equals -1/3 as well. Now I delete everything else and we can proceed. There's a particle, oh, well, we don't have to delete that, but even the partial derivatives in respect to x and y are useful, but I have them elsewhere, so I don't have to refer to them straight on the screen. We need more space on the screen now. And then plus yx, that's the accidentally deleted part. Now the font got slightly changed, but it doesn't mean anything. Let's just imagine the font didn't change. That was accidental as well. So we have x equals xy squared plus yx squared plus yx all along. Then we got these critical, so-called critical points. Again, this doesn't mean anything. This is we have these 2 points, and then there's a theorem that directly tells us how to take these points and see if they are a local minimum, local maximum, or a saddle point. Where local minimum, local maximum, quite clear, I hope. And saddle means basically it's a local minimum for one of the direction, for the y direction, for example, and for the other direction, in that case, the x direction, it would be the opposite. So it's a local minimum for one direction and a maximum for the other. That's a saddle point. So these 3 options, local minimum, local maximum, and a saddle point is what we're looking for in P1 and P2. We're going to see which of the 3 both of them are. So to find that, we need something called first H, which is the determinant of a particular matrix. I can write it down here quickly, I'll delete it. Basically, our function f, there's a matrix called the Hessian of it, and it's basically partial derivative twice in respect to the first variable here, then partial derivative twice in respect to the other variable, then here first in respect to the first one, then in respect to the other one, and then first in respect to the other one, then in respect to the first one. So this matrix, and then the determinant of it is the H that I have right here. But again, I'm going to delete it to gain more space, and we're going to write out the determinant. So that's the derivation, how we can remember this formula. So this H is namely f double derivative in respect to x times f double derivative in respect to y minus mixed derivative f sub xy to the second power. And you might ask, is it clear? Is it always so that the partial mixed derivative f sub xy is the same like the other way around, that first you derive in respect to y and then respect to x, so not f sub xy but f sub yx? No, it's not always the same. There's a lot of functions where it's not the same. There are many theorems relating those facts and telling you when you can expect it to be the same and when not, but we don't have to worry about it in this case because I verified for this function it is the same. The mixed derivative is the same. And most of the time when you're faced with the formula itself and you're not told about the Hessian matrix behind it, you're going to get this. You're not going to get option when you research for it. You will not see an option that the f sub xy squared is replaced by f sub xy times f sub yx. It's very usually written like this. So it's expected that they're same, the mixed partial derivative. But there are theorems telling you when to expect. And in this particular case, this function's mixed derivative fxy and fyx are equal to each other. So that's a saving factor, and that's why we can be certain that using the f sub xy is fine. So this thing is the h, and now this h can have different values, and it's quite general of value seeking because here the theorem steps in more. The theorem says that if h is more than 0, so the result of this is more than 0, then there's 2 more options. the second derivative in respect to x is either smaller than 0 or it's bigger than 0. If it's smaller, it's a local max, and if it's bigger, then it's a local minimum. So from this tree diagram we can find if that particular point is a local minimum or a local maximum. And then if it already starts with us finding out that h is smaller than 0, then there's one option, and that means it's a saddle point. So this is the tree diagram for this for the theorem. The theorem says that if the h we find using the second derivative we're going to get in a second, I'm not going to actually use the first order derivative that we already gotten before. They're not going to be on the screen anymore because they would take too much space, but I have them still and I will use them to get the second order ones. The h, if it's higher than 0, we then have two new options. It will either be a max or local minimum. And just to underline both, if already one is underlined, not to cause confusion unnecessarily. Then if the second order derivative in respect to x, only x, is smaller than 0, it's a local maximum. And if that same derivative, second order in respect to x, is bigger than 0, it's local minimum. But if in the beginning already h is below 0, that directly tells you without further work that it's a saddle point. It means it's a local max and local minimum for those two different coordinates respectively. And so you could also search online for pictures of a saddle point, how it looks if you graph out the 3D function. I think that's good for imagination of it, to understand or remember how that plays out, how that looks in practice. And so I'm going to delete this and suppose that you either write it down or have access to this tree diagram or this theorem. And now we're going to just use this theorem, applying it to both of the points, namely P1 and P2, to find out if they're a local maximum, local minimum, or a saddle point. So let's first consider P1. The second order derivative in respect to x is I take the partial derivative in respect to x I already had before and just derive that in respect to x once again. So that gives 2y plus 2y, but 2y. That's f sub xx. Right, the plus is unnecessary there. That was accidental. And then double derivative in respect to y. Take the first derivative in respect to y and derive it in respect to y once again. And you'll get 2x. So we see a pattern. So there are 2y and 2x respectively. And then the mixed one. I will not show that when you derive first y and then x, it's going to be the same result, but you can verify it for yourself. I'm just not going to write it here to save some time and space, not to have to delete it afterwards due to a lack of space. So f of xy, I'm just going to cut it off here because, yep. So f mixed derivative in respect to x and then y. I take the x derivative and then derivative in respect to y, so I'll get 2y plus 2x, 2y plus 2x plus 1. And the same plays out for if we did it the other way around. But I'm not going to show it, I'm just going to leave it here and use it. So what we'll now do is, first I'll take 0.1 and use the 0 minus 1 of 0.1 to get the h and see what that is. So I hope you have reference to that theorem somewhere, because it's no longer on the screen, we didn't have the space for it here. So this is definitely important to refer to. So I'm going to be using and referencing exactly that theorem. So now I'm considering 0.1, not writing it anywhere that I'm considering 0.1, but I'm considering the point 0 minus 1, that 0.1. And h will equal always second derivative in respect to x times second derivative in respect to y minus the mixed derivative squared. So that's 4yx minus the mixed squared. That's 0 minus the mixed derivative squared. And then we have to plug in minus 1 into the mixed derivative, 0 and minus 1 there. So it's minus 2 plus 0 plus 1. So it's minus 1 squared. So it's 1. So it's minus 1 here. So it's minus 1. And because it's more than 0, the theorem says that if h, the determinant of the Hessian matrix, is lower than 0, then directly we know that point is a saddle point. So I'll write it down here on the top right of the screen. Saddle point for P1. And now let's do the same process with 0.2, and I can already tell you because I calculated it before. The result for P2 will be longer to get to because we won't get a negative h, we actually get a positive h first, and then we have the two more options according to the theorem stated earlier. But yeah, so but let's show it. Let's get there methodically using the theorem. So the theorem again says h equals the second order derivatives to those respective two different variables multiplied by each other minus the mixed derivative squared. So again, 4yx, but now I'm plugging minus 1/3. So 4 times basically minus 1/3 to the second power is 4/9. So it ends up being positive actually. And then the second, then the mixed derivative squared. That's harder because we have a longer expression here. So minus 2/3 plus 1. That's minus 1/3. But to the second power, and that is basically 1/9. So that's only 3/9, that's fine. That's still above 0. So we have the two options as I said. So because h is now above 0, we have the two more options. The second order derivative in respect to s can be either negative or positive, and depending on that, you'll see is it local maximum or local minimum. So let's see. So f sub x now, we have to do it when h is above 0, the second step, is 2y, and y is minus 1/3, so it's minus 2/3, and that's smaller than 0, and so it's a local maximum. So I'll write it down here. So for point 2, we found out it's a local maximum. So here is our results. P1 saddle point, P2 local maximum. The way we got there is first we got the function f, we took the partial first order derivatives in both of the variables, set those both things to 0, solve for x and y. We got two pairs of x and y, 0, minus 1 and minus 1/3 twice. And then we use the theorem saying that if h is bigger than 0, where h is the determinant of the Hessian matrix the theorem I showed a couple of minutes ago, which is namely the second x derivative times the second y derivative minus the mixed derivative squared. If that is plugging in points from one of the points, so we're now doing for the point 1, so I plug in 0 and minus 1. If that is above 0, we have two more options, and those options namely are second x derivative. If it's negative, it's a local maximum. If it's positive, it's a local minimum. Then if this h in the first place was negative, we directly know that it's a saddle point, which happened for point 1. And for point 2, the opposite happened.